Well, hello there, Advanced Chemistry. Welcome to our Unit 2, which is going to be an introduction to thermochemistry. I love this unit. If you are looking for the learning targets associated with this unit, you can find them either in the shared folder from going to our blog and clicking on the shared tab, a shared assignments tab, or on Edmodo. I shared them in both places. There's also a reference sheet that you can find in both places that will be very helpful. So without further ado, let's jump into 2.1, which is understand energy and how it is used to describe heat transfer in a chemical or physical change. So we're going to start off by reviewing some things. So we're going to define energy. Energy is the ability to do work or produce heat. It can be measured in joules or calories or other things, but those are the two most commonly used and that we'll use in this class. And 1 calorie is equal to 4.184 joules. So energy is the ability to do work or produce heat. One thing that I would like to mention or remind you of is that energy has the ability to flow, but it cannot be destroyed or created. That's the law of conservation of energy. Very similar to the law of conservation of mass. So it's to do work or produce heat. Remember, if energy is released, from a system during a process, we call that an exothermic process. Okay, and if energy is absorbed, or sometimes you think of it as required, then that is an endothermic process. We used those terms last year. So there's energy. I want to talk now about the difference between temperature and heat. So heat is a form of energy. It says here that it is the sum total. So the sum total of the kinetic energy of all molecules in a substance. Or if you want to think of it as the system. So if you took the kinetic energy of every single molecule, added all of those kinetic energies up in joules, you would have the amount of heat in that substance. Temperature, however, is the average kinetic energy of all molecules in a substance, which implies that all molecules do not have the same kinetic energy. They have differing kinetic energies. So that's the difference between the two. And obviously heat, we remember, measured in joules or calories. Temperature is measured in degrees Celsius or degrees Kelvin. Remember, just because we're going to be working with it in this unit, that a degree Celsius is just 273 degrees less than a degree Kelvin. So the Kelvin scale is a degree Celsius plus 273. So going up 1 degree Kelvin is the same as going up 1 degree Celsius. And I know I said that backwards from what I wrote it. But they are the same amount. Like the magnitude of 1 degree is the same in both cases. They're just 273 degrees apart from each other. Okay. I would like to show you a visual representation of the difference between heat and temperature. So I'm going to draw for you on this next slide a graph that shows the number of molecules versus the kinetic energy of those molecules. So I apologize in advance for probably what will not be very straight lines. So here's my y-axis there and x-axis. And on the y-axis I'm going to have the number of molecules, implying that the higher you go, the more molecules have that energy. And so along the bottom, I'm going to have increasing kinetic energy. So in other words, here I would have very low kinetic energy, and here I would have very high kinetic energy. So it turns out that the molecules in a substance have a range of kinetic energy. So I'm going to use a yellow for this. So it kind of forms a bell curve. So if I were to think about some water that you spilled on your lab desk. So it turns out that those molecules all have different kinetic energies. So some are way down here in the low range, not very many, and then some have a very high kinetic energy, but most are right here, where I put that little tiny dot. And so if I were to average all of the kinetic energies, it would probably average somewhere around right here. So this would be your temperature, which would be the average. But the sum total would be if I took all the kinetic energies of all those molecules. So it would just be this huge amount. It would be all the kinetic energies of these molecules, all of these ones, all of these ones. And remember that the higher it is here, the more there are, so we'd have to add them up multiple times. So that's heat. Now let's say our puddle on our desk gets really cold in our room, so the temperature drops. So what that means is that the average energy of our molecules goes down. So you might think of that as something like this, where if the temperature in the room drops, we still have our bell curve, but now that average is somewhat lower. So the average kinetic energy is lower, which means the temperature is going to decrease. So the average kinetic energy of those molecules is down. So there are still some molecules that have more energy than molecules originally, but the average kinetic energy is lower. So that's the difference between heat and temperature. Heat is the sum total of all of the molecules' kinetic energy. Temperature is the average. Okay, just a review here, defining the system, surroundings, and universe in any process. I'm not going to spend a lot of time on this, so feel free to pause if you need to write this down. Our system is the process or reaction under study. This should be the surroundings, so that's an error. The surroundings is everything else in the universe, and the universe is just the system plus the surroundings. So this should say surroundings. What students have a hard time understanding with this is that a system can be a reaction. So an example I want to give you is your limiting reactant lab, where you had a beaker or a flask, I guess is what you had, and inside that flask you had some hydrochloric acid that was aqueous, and then you had a strip of magnesium. And so the system in this case would be the hydrochloric acid and the magnesium. That would be your system. So the surroundings would include the beaker, it would include the air above the reaction, but it would also include the water that is surrounding the hydrochloric acid and the magnesium, because water isn't actually taking part in the reaction that we're studying. It's surrounding it. So the surroundings would actually be a lot of this solution. All the water in this flask would be the surroundings as well. In that particular reaction, between the hydrochloric acid and the magnesium, energy was released out into the surroundings, so into the water, which was the immediate surroundings. So the reaction between hydrochloric and magnesium produced heat. So that would have been an exothermic reaction, which is why the water increased in temperature. So the overall temperature was increasing of the surroundings. So we could have measured that as a temperature increase. Oops. Okay, now we're going to dive into specific heat. just going to define it, and then we're going to do some calculations with it more on Monday. But the meaning of specific heat and know the units. So first, the definition. Specific heat, which is symbolized with a lowercase c, so that is the symbol for specific heat, is an intensive physical property that defines the number of joules required to raise 1 gram of a substance by 1 degree Celsius. So in other words, it's the amount of energy required to make the temperature, the average kinetic energy of 1 gram of something, go up 1 degree Celsius. So the units for this are the joules required per gram of substance per degree Celsius. So per 1 degree Celsius. So how many joules are required per gram per 1 degree Celsius? So those are your units. Or sometimes you will see joules per gram Kelvin. And since those are in the denominator and it's a kind of a pain, some people use negative exponents like joule, gram to the -1, Kelvin to the -1. So instead of putting them in the denominator, they write it as a negative exponent. So that's specific heat. So before we wrap this up here, I kind of want you to think about this. If you've ever gone to the beach on a really hot day, so bear with me here. You go to the beach on a really hot day. It's Lake Michigan. And you run from your car and you're really excited and you go down to the beach and you hit the sand and you already took your sandals off. So you've got your sandals off and you're running to the beach, and I'm going to use gray to show the sand even though sand's not really gray. So here's the sand, and here's the water. Okay. So as you come down along the sand and your sandals are off, they've been sitting out under a sunny sky all day. So they've been exposed to the same amount of energy as they've been sitting out in the sun for the same amount of time. So when you hit the sand, your feet hurt. It's hot. It hurts the bottom of your feet. But when you dive into the water, if it's Lake Michigan, it's really quite cold in comparison. So the answer to that, my dear friends, is specific heat. So it turns out that the C for sand is very small. So the number of joules it takes, so the amount of energy it takes, so joules, remember, comes from the sun, the amount of energy it takes to raise 1 gram of sand by 1 degree Celsius is pretty low, meaning it doesn't take a lot of energy. So this energy from the sun can be used to increase the temperature more. So this is going to have a higher temperature because those joules don't have to be used as much to increase that temperature. So that temperature can go up really high. But for water, the number of joules it takes to raise the temperature of the water, it takes a lot of energy to do that. So it's not going to heat up as fast because it takes a lot of energy to raise every gram of that water by the same amount, by 1 degree Celsius. So water is going to heat up at a slower rate than the sand. So I'm going to leave it at that, let you kind of mull that over. So the C, the lower the C value is, the faster that temperature is going to fluctuate. And the higher that C is, the slower it's going to do that. Now, we're going to talk about this more on Monday in the beach situation, so keep that in your brain. But for now, that's it. This is Mrs. Sharp signing off. I hope you have just a wonderful weekend and get those lab reports done. So I will see you soon. Adios.